Hi, welcome to the Signal Path. In this episode, we're going to talk about high voltage signal generation. Actually, a topic we haven't really talked about much here on the channel, but I have an instrument here which is pretty special, and I don't want to give away the engineering that's gone into it because we have to build upon a few steps to really appreciate what's going on in there. But there's a lot of experiments, a lot of theory, and a lot of practice here at play. I think you're going to like it. Let's get started. So let's consider that you're an engineer and you're given a design problem to make an amplifier with a particular set of specifications. In this case, it's a simple one. It's a single-ended input, single-ended output, and it has some gain and bandwidth characteristics. So the gain is about 2000 volts per volt, 66 dB, which is pretty trivial. You can easily get that with modern op-amp. And a DC gain accuracy of 0.1%, you should be able to do considerably better than that with appropriate feedback around it. Then a small signal bandwidth of 20 kilohertz, that's really nothing because this is within audible range essentially, so that should be pretty easy to do as well. Input impedance 25 kilo ohm, that again can be really easily met, particularly if you have a FET input, for example, even a bipolar input, you can easily get much better than 25 kilo ohm. Now output drive of plus or minus 20 milliamp, well, you're going to have to start burning some DC current to make sure that the output buffers of your op-amp have enough driving capability to deliver plus or minus 20 milliamp to a particular load. Even though the load is not mentioned here, but if you short the output, you'd want to be able to get this much current. Slew rate of 350 volt per microsecond, pretty easy considering the bandwidth that we're dealing with. Distortion of better than 1%, that should be really easy. In fact, 1% distortion for an audio amplifier is pretty bad unless you're putting out a lot of power. And now we get these last two components here. Put offset voltage of plus or minus 2 volt, well, that's actually pretty terrible. It should be easily better than that. And output noise of 5 volt RMS, and you should be able to do significantly better than that, at least 1,000 times better than that, even with basic design. So what makes this all challenging? Well, it's not so far, but I can add one more specification to this that completely changes how we look at everything else here, and that is the output voltage range. Let's say that this amplifier needs to be able to deliver plus or minus 20 kilovolt to a load. Now all of a sudden these two numbers make a bit more sense because in the context of 20 kilovolt, having an offset voltage of 2 volt is not so terrible anymore. And let's say we want to meet this kind of output criteria where you can do load sinking and sourcing, essentially be able to do this in 4 quadrant as an op-amp would be able to do. But then if you're sitting here, now this 20 milliamp output current becomes a lot more meaningful because 20 milliamp at 20 kilovolt, that's 400 watts. That's a lot of power that you're putting out, and also a lot of power that you'll be absorbing if you're operating in the other quadrants. And this gray area is the AC area and the dashed area is the DC. So the AC is a bit more constrained into sinking and sourcing with positive and negative voltages, but the DC occupies all 4 quadrants. So now all of a sudden, because of this 20 kilovolt, this becomes significantly harder to design. In fact, a linear amplifier that has the output how much voltage is already very, very hard. So that's what I wanted to really discuss. And how do we get there? What kind of circuit topologies and architectures are required? And what do we do in general to generate high voltage? Let's take that one step at a time. Now, the easiest way to generate very high voltages is to wear rubber boots and walk on carpet. But if you want, you can also use a transformer. A transformer would allow you to scale the current or the voltage on the secondary depending on the turn ratio between the primary and the secondary coil. So for example, if I put a sinusoid at the input of this transformer and I increase the number of turns on the secondary coil to be much higher than the primary, I will get a sinusoid of much larger signal amplitude on the secondary coil. Now this gives us voltage gain, and that sounds great, but of course this is a passive structure. It will not give you power gain. So as an amplifier, it's not really doing what we want it to do. For example, if I load the output of the secondary coil here with something that requires a lot of current, that actually translates to the input impedance of the primary changing because the transformers are coupled together. As a result, the amount of power I get at the output will always be less than the amount of power I put in because it's a passive structure. And even if the transformer were ideal, it would only become 1-to-1. There are many other problems. A transformer would not go down to DC, so we will not have DC gain through it. And even if we could make a transformer extremely large to go to very low frequencies, the core would become so huge that it would not work at higher frequencies, aside from it becoming completely impractical. There will also be magnetic flux saturations and other problems with transformers as a result of that. So even if we could solve the self-resonance frequency problems of this, we would still have to deal with the extremely difficult breakdown problem of generating plus or minus 20 kilovolt on the secondary side of this transformer and the isolation to the primary and so on. And just building something like this that can handle such a large voltage would be a challenge. If you ever watch any videos of people building Tesla coils, for example, you see how difficult it is to make sure that the primary and the secondary door arc together and they don't just destroy themselves as a result. Now, having said that, obviously transformers are used everywhere, including high voltage power supplies. And perhaps the most common use of it on a day-to-day basis is in a microwave oven. And these things have been built down to the lowest possible cost, and all the circuitry basically looks the same nowadays. You do have your main high voltage transformer, and a city line comes in, and there are two secondary coils, one over here and one over here. One of them is very low voltage, and it's just used to heat up the filaments, and the filaments then heat up the cathode for thermionic emissions inside the magnetron. This whole thing is a very fascinating device. We can talk about it on a different video. But on the other side, we do have a high voltage fuse. These high voltage fuses tend to be quite long and even spring loaded, so that when they pop, they separate from each other to avoid arcing inside of the fuse container. An interesting device itself. And then we have a high voltage capacitor and a high voltage diode. Then the combination is just a simple doubler, and it gives you a DC voltage, or I should say a doubled voltage here at the magnetron to generate the signal that you're looking for, the RF signal for heating up your food. And the circuit essentially looks the same everywhere you look. And these transformers are everywhere, and people take them out of the microwave oven and build all these super dangerous things with them. And if you've ever seen videos, people make all kind of arcs and various things with them. Extremely dangerous. These things are lethal because there is no protection. If you touch the output side of this transformer by mistake, 2000 volt, there's no limit, there's no current limit. It will absolutely destroy you. So you have to be super, super careful with these. So let's take a look at a couple of instruments that I have that do generate high voltage in different ways before we get to our ultimate amplifier design challenge. Now, having said all that, it doesn't mean a simple transformer high voltage power supply isn't useful. In fact, it can have some self-regulating characteristic, which is helpful. So this is a really, really old high voltage power supply for turning on various noble gas lights. I'll show you that in a second. And if you look inside, there's really nothing in there. It's just a very basic transformer. And this effect can also be had with a transformer in series with a resistor at the output side too. But let's see what this does, because this will have a certain open voltage when it is not connected to anything, and then it will have a certain voltage when it's under load. And they can be quite different, which is very helpful for various gas discharge tubes or anything that has ionized gas in it because of its resistance characteristic, which we will see in a second. Let's connect it to some load. So the output of this power supply has a terminal like this, which connects to these various tubes. And I have a couple of them here. This one has mercury gas in it. I have one that has xenon in it. And I think I have one that has argon in it. There's a few more with neon and so on, different kind of gases. Now these are used to create very predictable spectral lines optically. And I may have shown some of these spectral lines of various gases on the channel before. These are very good for various physics experiments, or if you want to calibrate the spectrometer, you can certainly do it with this, because you know exactly what those lines would be. They're a function of the atomic structure of the gases, molecular structure, so that's never going to change. So let's try something like this. Which one is that? This is mercury, so we should be able to get some nice UV out of this one. Plug it over here, and I can see it doesn't even completely go in. This is a really old unit. There you go. Look at that. There's go. Some nice UV coming out of this. It's going to probably create some ozone as a result of this. I'm not looking at it directly, but yeah, you can put this in front of the spectrometer and see nice tones in there. Let's turn it off. Let's try a different one. And this one is argon. You can see a little bit of purple pink color to it. Looks quite nice actually. And the reason these are difficult to drive is because you would need a very high voltage to strike this tube, so to begin the flow of electrons and create these photons that come out of it. But then once that ionization happens, the resistance of the tube drops drastically by orders of magnitude. And if you apply the same thousands of volts across it under that condition, you would burn a huge amount of power in this tube. So you need to drop the voltage immediately to not destroy the tube. And that's where the self-regulation happens. In fact, we can measure that. We can measure the open circuit voltage, and we can measure it when it's under load and the tube is already lit. And then you can see the difference, which is quite big. Let's try it. So let's go ahead and use the Vitrek 4700 to measure this high voltage. I bought this from eBay for the purpose of making this video, and I was surprised how expensive these things become on eBay. I think I paid over $2,000 for this. Who is buying these, and what are they using it for? If you're using one of these for your regular work, let me know. But these are really nice high voltage measurement devices, and it would be a subject of its own video, because measuring high voltage accurately is a whole other problem. So I have it connected right here directly to the output. You got to be very careful. Again, we're talking about multiple thousands of volts, and then we can turn it on and see the open circuit voltage. All right, turning the power supply on. And check it out, we get 2.27 kilovolt, and we get almost no DC. That's to be expected. This is a transformer. It's not going to create any DC voltage. The frequency is written over here, 60 hertz, which makes sense because it's just using the line voltage, peak to peak 6.6 kilovolt. That's a lot of peak to peak, and a crest factor of 1.4. Yeah, it's a nice sinusoid coming out. Nothing unusual about it, but let's see what happens when we load it. So same situation, except that now the tube is directly connected and we're monitoring across the terminals of the tube. Turning it on, look at that, we're getting only 268 volt RMS, but the peak to peak is like 2.3 kilovolt, and the frequency comes and goes, and there's even a little bit of DC. But this is an example of how self-regulation can happen using a transformer if you don't care about the shape of the waveform at all. Now, interestingly enough, you don't have to build a precision high voltage source to make a precision instrument. And maybe the Fluke 1587 FC is a good example of that. This is an insulation multimeter with a high voltage power supply built into it that can put out up to 1,000 volts. And then you can measure the current through some unknown load, and it can tell you how good the insulation is, up to hundreds of mega ohm, which would be difficult to measure with a lower source voltage. So right now I have set it to 50 volts, and I've connected the two inputs together like this. So we're just simply going to use this Fluke 289 both as a multimeter but also as a load because it has an input impedance of 10 mega ohm. Let's go and measure that. So if I hold this, it's going to apply, and look at that. If you look, it's not applying 50 volts, it's applying 55 volts. It's not even close to 50 volts. And the reason it does that is because it just generates something that's up to 10% of where you should be. And then it has a precision built-in multimeter, of course. So it's just going to measure its own voltage and measure the current and figure out the load, instead of trying to make a really accurate high voltage power supply. Now this goes all to 1,000. Let's go up to 1,000 here and try it again. Let's see what happens. Look at that, it's generating 1046 volts, so it's quite a bit off again. But look at that, the input impedance is 8.3 mega ohm. It's no longer 10 mega ohm. Now you may be tempted and say, well, probably electrons are being lost through here because you're applying 1,000 volts, so it's going to show up in parallel, and those lost electrons are going to look like that the input impedance is lower than 10 mega ohm. But let's try a different multimeter, you'd be surprised. Okay, same situation, except I'm going to use the Keysight U1282A now, and it's the same cable I was using. Let's try it again. Holding that. Look at that. 10 mega ohm exactly, and it's measuring 1,047 volts. So yeah, so it's not because of that. What I suspect is going on is that the input protection of this is beginning to kick in because this is not really supposed to work above 1,000 volts. So the impedance begin to generally drop ever so slowly, and eventually at some point the input protection will kick in and probably shunt the input, or maybe a spark gap will shunt the input. So I think that leakage might be internal. Let me know what you think about that. But this is an interesting example because it's clearly measuring the internal voltage over here and using that with the internal current to tell you what the resistance is. But it's not applying 1,000 volts at all, it's applying anything that's close. So an interesting example of a not so accurate high voltage power supply used for precision measurement. Now, making a high voltage AC or DC power supply that's both accurate and precise under variable load is considerably more difficult because now you will have circuitry that have to operate at those high voltages. But generally speaking, a DC power supply for a few thousand volts is not very challenging. This particular one is a Stanford Research model PS350. This is a 5,000 volt 25 watt power supply, and you can set the output voltage in 1 volt resolution step. I have the output connected to our meter at the top, and we can turn it on and see how it looks like. It's set to 5,000 volts, and it does give us the output current, which is quite helpful, and the live output voltage, the readback directly from the circuitry, taken from the feedback network, of course. Let's go and turn it on, and let's see what it does. It should stabilize at 5,000 volts quite nicely. There it is. The output has reached 5,000. Look at that. I mean, that is pretty good, and you can change the load, and it would go up to 25 watt maximum power. Now, these kind of power supplies do not work well at very, very small voltages because their output divider network is not adjustable. It's only a fixed division ratio. And at some point, you're just simply going to run into the noise. So, for example, if I set the output to 0, you can see that it will drop down, but it will never quite go to 0. It'll probably hover around 30 volts or so. As it's stabilized. Yeah, see, it doesn't really go below this. And just, you can see if I turn it off, it does actually go to nothing because the DC-DC converter is turned off. If I turn it back on, then the lowest it can produce is about 30 volts. So if I go over here, for example, and ask for 50 volts, it should stabilize nicely to 50 volts. Man, that's a reasonably good job. Look at that, it jumps around a lot, but you know, it's fairly stable at the output. So let's take a look at the circuitry and see how this instrument actually works. They all start from the same fundamental principle. This is still just a DC-DC converter. And then we have a transformer with a high turn ratio. And then there's a drive A and drive B port on this transformer on the primary side. And they basically essentially put a square wave with inverting signals on top of this primary port, and that's going to induce a current, and it's going to get a very large voltage appearing on the other side. Now, the three models of this instrument all provide the same amount of output power. They can only do 25 watt, but of course, as the voltage goes up, the amount of current they can provide goes down, and that's because the way they achieve this using diodes and capacitors is a little different. For the lower voltage model, the 1250 volt one, they basically use a full bridge rectifier, and the full bridge rectifier goes into a smoothing capacitors. You get yourself a nice DC voltage, and then you have this mechanical switch in the back which you can switch the polarity. So this instrument is not electronically capable of switching between two quadrants. You have to manually switch it, and it's really important that when it's running you don't switch it while it's active, because all these capacitors on the output side are all charged, and if you swap this, you mechanically take two capacitors, each let's say with 1250 volt on them, you flip them and you connect them back together. So a huge amount of current is going to flow through this and destroy everything. So they explicitly tell you to make sure you do not do that. But the rest is pretty obvious. Afterwards you have the voltage dividers, which are used to sense the voltage coming back, and then there is the resistor in series to sense the current. Now this I sense and V sense can then be used to tell the user what the current consumption of your DUT is, which is connected to this port. But the V sense is used in a negative feedback system. So this signal goes back over here and controls through a bunch of other circuitry how these signals are applied to the transformer. And that's how the regulation happens. Very similar to basically any DC-DC converter. And as a result, this is going to operate in a continuous loop. And if you break this loop, you're going to get some wildly changing voltages at the output side of this circuit. Now, in order to reuse this front end and all the other circuitry that's inside of this unit, they can just change the way this rectification works in order to achieve higher voltages. And that's exactly what they do for the next one up. So this is the one that goes to twice the voltage, 2500 volts. And if you look, all they've done is that they have added a voltage doubler. So instead of a full bridge rectifier, now we have the voltage doubler achieved with D1, D2, C1, and C2. The rest of the circuit fundamentally stays the same, except the voltage division ratio has to change because now you have twice as much voltage, and then you have to make sure that all these different capacitors and diodes that you're using are now rated to the higher voltage in the circuit. Now there's one other thing they can use iSense for, and that is to detect trip, so that if it goes over 25 watts, this input basically stops. The inverter no longer applies signals to the transformer and the whole output gets disabled, and the user is then told that, okay, the circuit has tripped. It's a pretty nice safety feature, but both of these, iSense and vSense, have to be simultaneously used. Now if you want to reach 5000 volts, you don't need a doubler. Now you need to multiply by 4, you need a voltage quadrupler, and that's exactly what they do in this final version of this. Now if you notice, everything else is now rated to 6000 volts. This thing goes to 5000 volts, but here you go. Now you have twice as many diodes and twice as many capacitors. You quadruple the voltage. But of course, all of this means is that you're going to get half as much current as you could get from the 2500 volt version, and 1/4 of the current you could get from the 1250 volt version. That's because there's no magic here. These voltage doublers with capacitors and diodes just simply trade off current for voltage and vice versa. That's all that you can do really with these things. Essentially, the power remains constant, but it allows you to go to higher and higher voltages. You can go even further up, but I don't think that I don't believe they have a version of this instrument that goes above this. But that's it. That's really all they do. Some of the protection circuits become harder and harder to design at the output. Now we can go ahead and play around with it a little bit more, but keep in mind that this is still only 5000 volts. The difference between 5000 and 20,000 for semiconductor materials, capacitors, and everything is quite large, and it's a much more difficult problem to solve at 20,000 volts. Not to mention that this is just a DC voltage. It's not an amplifier. It cannot provide AC voltage at all anyway. And here's a close look at the high voltage portion of this 5000 volt power supply. It has a cover. I've taken everything off so we can just quickly take a look at it. The inverter input comes over here, driving the primary side of the transformer, and the two outputs that go out over here go through the voltage quadrupler. So the voltage at this point is 1/4 of the voltage that will be developed at DC at the output. Basically, the AC to DC conversion also achieves the quadrupling of the peak voltage value. On the other side, we have all the capacitors that are part of the voltage quadrupler, and we do have the output capacitor over there. This thing needs to be able to be rated for 6000 volts. And you can see that the output high voltage terminal does not look like a normal one because of the extended cover that it has here, and it can definitely support the high voltage outputs. But this is nothing compared to something that's supposed to be able to do 20,000 volts. And here's the switch over here that flips the polarity and gives you negative voltage below the case ground of this instrument. So everything matches perfectly to what we saw in the schematic. And all these resistors will make up the voltage divider as well as the current monitor. Yeah, looks nice. We just have to make sure we put it back carefully because obviously this needs to be very well protected. So let's do a quick experiment taking advantage of the trip and current monitoring capability of the power supply, which can be quite helpful in overloading conditions. So here at the top, I have a strobe light, and these strobe tubes are intended to produce a lot of light by passing current through an ionized gas. Now if you look, almost all of them have 3 terminals. There are the main 2 terminals on each side, that's where the current flows, and there's a 3rd terminal sitting in the middle that doesn't go inside the tube, it just has a ring around the outside of the tube. And that's because you need some way to strike the tube so you can begin the flow of the current. So in those situations, they basically put a couple of 100 volts across the 2 main terminals, perhaps by charging a capacitor, and then they briefly apply thousands of volts to the middle port, and that strikes the tube, begins the current flow, and then the resistance of the tube drops drastically, and that's how the current discharges through it, and then the capacitor discharges the tube. If you put thousands of volts across it, and there's a lot of power behind it, you would blow up the tube as soon as you strike it because the resistance will drop, as we saw in the previous one where we had a self-regulating system. So in this case, I'm going to apply 4,000 volts directly to the outside terminals. We're not going to use a 3rd terminal, and it will ionize by itself. The resistance will drop, and the power supply should protect us, I hope, in the case of this situation. Let's go and turn it on. And here we go. Look at that. We got a spark sitting at 4,000 volts, not enough to ionize. Let's increase it to 4,500. There it is. It tripped. Let's try again. Look, it does a couple of times, and then we get the trip function. So it's very helpful in protecting the tube. It's kind of cool, actually. Look at that. Now, if I go ahead and reduce, it's not 4,500 is not striking again. Let's go to 5,000. Ooh, power trip. So that was a big discharge, and now I went over power trip as opposed to the I trip, which is the worst condition actually for the power supply. But it is protecting us. And a close look at the tube. Quite nice. Unfortunately, you would need a really, really high-speed camera to really see what's going on. Nonetheless, looks pretty neat. Now, probably one of the most common use cases for a high-voltage AC or DC power supply is a HiPot safety tester, where you apply a very strong electric field by applying a very large voltage to make sure that things don't actually break down. This can be very helpful for safety reasons. For example, you may have an instrument that the user is holding, and that user is plugging this instrument into the wall socket. You want to make sure that if the wall socket has a surge, thousands of volts, that it wouldn't find its way to the end user, or that its devices can actually survive and won't arc over. As a result, these things are sold from many different brands. I have a Vitrek one, the same brand as the multimeter up there. Now, this particular instrument can only apply AC or DC, and we will see why when we do a teardown. But I have it configured to do 2 different tests. To apply a 5,000 volt AC with a 10-second dwell time and a 5-second ramp up, meaning that it will take 5 seconds for it to reach 5,000 volts, and it will hold that for 10 seconds and then ramp it down. And then it will apply a DC voltage, also 5,000 volts, we'll do the same thing, hold it for 10 seconds, and then bring it back down. This is a very simple test. There are many other different configurations of tests you can do, but this can only go up to 5,000. So let's run it, and then we can take a look over here and see what happens. It's interesting that when everything is turned off, there's a 20 volt AC coming out. Must be just picking it up from internal transformers and everything else. Here we go. We start this test. If I can do that. There we go. So the test is running. You can see it's ramping up, and this is also ramping up, and it's going to reach 5,000, and it's holding it now for 10 seconds. Look at that. 5,000. It's not very stable, but it's good enough for the purpose. And the frequency is fixed at 60 Hertz. That should tell us something about the architecture. The crest factor was 1.4 and 14 kilowatt peak to peak. Now it's doing DC, 5,000 volts. Look at that, it switched to DC. Exactly the same. There's no more AC now. AC is almost insignificant. Drawing some current, 44 microamp, going back into the multimeter, just like the Stanford Research power supply was doing. Look, and it says that everything passed. If I show the detail, you can see that during an AC, we're consuming 22 microamp RMS, and over here, 44.5 microamp into the power going into the multimeter. It all works, and everything passed because obviously this is rated for 10,000 volts. You should have no problem measuring that. Now you may be wondering what these other ports are here at the bottom, but they are to measure the integrity of a ground connection, for example, to a chassis. In many situations, the chassis of an instrument is grounded, and therefore if there is ever something shorted to it, the fuse would pop because the current will go through the ground, and then the fuse will eventually probably go over the amount of current it's supposed to have. But now imagine if that ground connection is made with a very skinny wire, something that would pop, let's say, with 100 milliamp. In that situation, a short condition would just simply burst open that line and the chassis can become live. In this situation with this one, they apply 10 amp through a chassis to make sure that its resistance is very small and it can maintain that amount of current to go through it. It is also part of the safety test. So now let's try stress test something that was never intended to operate with 5,000 volts across it. Here I have a tiny little audio transformer, and this transformer has its primary terminals shorted together and a secondary terminal shorted together. We're going to apply across that, which means that a strong electric field will be present between the primary and the secondary coils, and it has to be able to take that strong field up to 15,000 volt peak to peak or so. Here we go. And it didn't survive that. What a surprise. 2045 volts, you saw some sparks in there. It says breakdown detected, and it basically took 15.8 milliamp peak, which was the breakdown voltage that this instrument can support. And you can see the test has failed. So yeah, this kind of thing can happen. And here is what's inside of this HiPot safety tester. Now, as you saw, this instrument can either give you AC or DC, never at the same time in any combination. As a result, the output is essentially a reconfigurable high voltage selector. You either send the AC signal through or you pass it through a very simple rectifier to give you the DC voltage. So as a result, this is still significantly simpler than the amplifier we're working our way towards. Underneath this main PCB are a few toroidal transformers, and that provide the energy for the final transformer as well as for the ground testing that this instrument also has. Over here we have a DC-DC converter for most likely just the electronics, and we have the driving circuitry through these purple wires that drive the high voltage transformer here. This big wire that's coming out, that's the high voltage output. It actually has two high voltage outputs, it looks like, and one of them might be used for the DC, one for the AC, or perhaps there are two different ranges of power coming out and the voltage coming out. And these big Dolum relays, these are 10 kilovolt relays used to switch between AC and DC, I believe. And then there is a 15,000 volt diode here, which looks like forming a very simple rectifier. So basically by switching that through, you get your DC voltage output. And this is the output of the main thing going over here to the main output of the instrument. There's a high, very, very high resistance feedback. That's probably part of the voltage divider. So overall, this is only the high voltage section. The rest is just digital feedback, measurement, and so on. So yeah, not that complicated, but still quite difficult to put together because of the very high voltage design of this. This is still only 5,000 volts, very, very far away from 20,000. But nonetheless, we can learn something about by looking at it. By the way, this is obviously not plugged in anywhere. I'm using a metal pick to point at everything. It would be dangerous even if this were not a 5,000 volt power supply. So now that we talked about high voltage power supply, some of their applications and how they are built, let's think about how to build a high voltage amplifier, which is a considerably more difficult problem. Now imagine a situation where you have a 20,000 volt power supply on one side and a minus 20,000 volt power supply on the other side. Whatever you put between these two power supplies as an active device has to now be able to withstand this 40,000 volt differential, so a strong electric field between these 2 points. Now generally, it doesn't really matter whether you use a solid state transistor or use a vacuum tube, everything is going to have some level of breakdown that you have to overcome. Generally, without getting into semiconductor physics, solid-state devices, their breakdown gets worse as transistors get faster. It has to do with the fact that you're shrinking things down, the dimensions are smaller, and naturally breakdown gets worse. Other things change too. But in general, it's very, very difficult to build transistors that have tens of thousands of volts of breakdown across them. So we have to make the problem a little bit simpler. And we can do this by putting a long chain of transistors between our two power supplies. Now this sounds simple on the surface, but it will have its own challenges. So let's think about that. In this situation, I've only shown 8 transistors, 4 NFETs and 4 PFETs. That means that the 40,000 volts between these two nodes is going to get divided among these transistors as everything is just biased and sitting steady state. So now I want to create an output voltage. In that situation, I have to apply a signal to the gate of these transistors in such a way that none of these transistors ever goes into breakdown. Now remember that this is called a stacking architecture. It's not a cascade. In a cascade architecture is a very specific combination of a common source and a common gate amplifier where you basically bias the gate of your common gate amplifier as an AC ground. In this case, that's not what you're doing. All of these gate voltages have to be driven with some signal from the outside. And if you think about that, that's because if I fix any of these gate voltages, let's say I go ahead and fix this voltage to some fixed bias and DC, and I apply no AC signal to it. Well, as soon as the output begins to swing up and down, at some point when the output is at this point, you're going to have a massive voltage difference between this drain and this gate, because this gate is a fixed voltage, and this transistor will simply immediately go into breakdown. So we can't do this. We have to apply a signal scaled appropriately to every one of these transistors' gates. So the biasing network that sits over here and applies the input signal to all of these now becomes considerably more complex. By the way, this stacking architecture is used inside of semiconductor transistors to build power amplifiers too, even at millimeter wave and higher frequencies. It's a common architecture. Here, we're dealing with a much harder problem because of the high voltages. So there are other few things you need to worry about, because the worst case scenario is not when the output is sitting at 0 volts. The worst case scenario is when the output has reached one of the power supplies, because this swing is going to be large. It's going to go all the way down and all the way up like that. So at this point, the output is sitting at 20,000 volts, and at this point it's sitting at minus 20,000 volts. When the output is sitting at 20,000 volts here, all these transistors basically have no voltage across them. They're all into deep triode. This is a class B amplifier, which means that the 20,000 volt is now going to have 40,000 volt across the bottom transistors. So each of these substructures has to take twice as much voltage before it breaks down as when the output is at 0 volts. So that needs to be taken into account. The opposite is true, of course, when the output is sitting here at minus 20,000, then all the burden of the voltages are sitting on this one. So you need a very complex and cleverly designed circuitry over here so that the input is applied in this situation here. It's divided appropriately to all these transistors before it reaches the output. Now, because some of these gate voltages still need to sit at tens of thousands of volts, especially the ones that are close to the power supply, they need to have a very, very high voltage on them, which means you cannot directly connect this. You cannot galvanically connect them. So all this network has to be optically isolated, which makes the whole thing even more complicated. And that's exactly how this instrument is built. All of this cleverness is inside of it. And here's the simplified block diagram of this instrument, and right away you will recognize the similarity between what I just showed. So this section right over here is what I had drawn on the previous slide. So here's our high voltage positive power supply, here's our negative power supply, these are the plus and minus 20,000, here's the output, and here's that long stack of transistors. In this case they're showing them only as 4 pieces. Each of these is actually an individual card, and as you can see they're all optically isolated and driven. And then the output of that goes into a precision resistive divider, which itself is very difficult to do, because remember, this voltage goes from plus 20,000 volts to minus 20,000 volts. So you have to make this completely custom made. And then after that, the signal comes back and goes through an amplifier in here, and this entire chain is in feedback. So you basically are building a giant op-amp and closing the feedback all around it. Now, this precision resistor divider is pretty important because it sets the gain and it sets the linearity, gain linearity of this entire amplifier stage. So now you have an input signal. Its input impedances can be pretty high. It can be determined by the resistors that you put over here. And then you have the feedback network, and this feedback brings the output impedance to be very, very small, as is any feedback with shunt feedback at the output. And then this signal can then be monitored, and then it would represent directly the output voltage appropriately scaled by the precision resistive divider. So that's the architecture of this instrument. As you can see, it's very different from a power supply, but hopefully by now you can roughly at least understand what is a trick that makes this thing work and how clever the whole architecture is. And finally, here's a look inside of this high voltage amplifier, and we get to compare it against the block diagram we just went over. It's a beautiful piece of engineering, and I've taken the top cover and the bottom cover off, and there's some light behind it so you can see the individual high voltage sections. Nothing's plugged in, of course, and this will not enable its output even if it were plugged in, because it has interlock switches on the top and the bottom cover, because everything in here is lethal. So you have to be super careful. Now, this instrument is made of 3 main parts. We have the front, which is where the human interface is, except for the high voltage section, amplifier input, the output monitor, things like trip and current limit, and interlock switches are all handled by this main board here. And this main board also drives all the subsections of that stacked amplifier stage I showed you. You can see that this wire over here, everything is in series in the positive and the negative section. Now on the right side, we have 2 big power supplies. One is a negative and one is a positive. I think this is a positive power supply and this is a negative power supply. At the bottom there is some rectification, 2 big capacitors to smooth everything out and provide a good stable power supply to these 2 other power supplies, because this thing is obviously not running at 100% efficiency. So if it can put out 400 watts at high voltage, it's burning a lot more overall. So it's a pretty power hungry instrument. And this whole thing is sitting on a big piece of plexiglass, these power supplies, because everything is floating. 20,000 volts or 25,000 volts plus and minus, not to mention that all these sections of the amplifiers, everything is floating with respect to ground. So super, super dangerous in many ways. The 2 outputs of this just simply feed the top and the bottom of this stacked amplifier chain, which we will see from the other side. The bridge rectifier feeding these capacitors, as I said, smooths everything out, and these power supplies are fixed. 2 big fans just blow over them. So the magic all happens in here. So you're just providing power to this big stack, and then this guy drives them, and everything has to be isolated optically. So let's look through this so we can see how these stages are made. And here we can see all the stack stages. So from the very top all the way to the very bottom. There are 10 of them, so the voltage divided among 10 of them. But at 40,000 volts, when there are only 5 of them, so you're looking at almost 10,000 volts per stage here, which is a lot. So if you look closely, you can see a lot and learn a lot about how they've put this together. So this cable in the front connects to the low voltage side, which is this port over here. Now they need to get this and couple it somehow into each of those high voltage stages and then appropriately divide the signal to be able to drive the final stage. And as I mentioned, they cannot do that galvanically. So if you look carefully, you can actually see that there's a little LED in the back and there's a light pipe. And they're using that light pipe to basically send the analog signal over. And all of these diodes vertically have a certain offset associated with them, so they all drive these stages simultaneously with the appropriate offset voltage. So if I move the camera over, you can see the transmitter side. Look at that. It's just some homemade light pipe that they've put together. And look at these big cuts in the PCB to isolate everything. Because remember, that stage over there, tens of thousands of volts above and below ground. So you really have to be far away from each other to not produce any arcing. Now each of these stages themselves are quite complex. They're made of several stages themselves. They're not in one amplifier. You can see many things. But this is repetitive. It's a structure that's constantly repeated. So if you look at how many stages are actually in there, from top to bottom, if I'm counting correctly, it looks like inside each of them there's like 10 maybe. So there's 10 times 10. There's like 100 things in series ultimately to make this thing work. Really incredible piece of engineering. You can zoom in a little bit more. You can see how many stages there are and how repetitive that structure is. Now at the very back, the final stages are still fairly high voltage. Each of those has to swing thousands of volts. And you do have those metallic caps, very classic high voltage, where if the voltage exceeds a certain amount, they can arc to each other, but they don't have a very sharp corner. That allows that breakdown to be quite a bit better. And there's a whole bunch of them. Each stage has a few of them. You can see there's so many in every place. But yeah, it's an amazing thing that somebody said, you know what, that's how we're going to put this thing together. It must have been a crazy proposal at a time when this was initially conceived. Now look at these plexiglass layers. They're all glued together, multiple layer of them, because on the other side we have such a high voltage. Unfortunately, this cannot be taken off very easily. It looks like they assembled this whole thing and they push it into the unit. And I don't want to take it out because it's going to be very hard to put it back together, and it's a risky instrument to play around with anyway. But yeah, let's take a look at the high voltage side. And here are the two fixed high voltage power supplies. So these are probably the least interesting part of this entire instrument, because they're just simply a transformer, just like the other instruments we saw produce and rectify and create a single output. Now this is still at 20,000 volts, so that is certainly different than what we were seeing before in terms of being only at 5,000 volts, but really they're doing the same thing. And there's two of them. It's the big capacitors at the bottom. And look at how much attention there is to the wiring. Everything's so careful, everything's capped and glued, and the bleeding resistors are there, all the wires so nice, so nice. Somebody put a lot of passion into putting these things together. Clearly very custom made. Now looking from the other side, you can see the highest voltage section a little bit better. And these pillars that you see, aside from being a good high voltage isolation and arcing and so on, they're also heat sinks from the final stages, I think. Yeah, if you look over, you can see all those white wires are the wires that connect the final output together across all the different vertically stacked stages together. At the very top, this line over here has come from the power supply, probably the positive one. And at the very bottom, there is an equivalent one. We'll look at the other side of the instrument so you can see a little bit better, because you can't see the output network very well from this side. But yeah, everything totally handmade. Now looking at the bottom of the unit reveals that there are actually two light pipes per section. There's another one here closer, and then one at the far back that you can see. But yeah, they look very similar to the other side. So perhaps they're either dividing the signal there, or maybe it's bidirectional. Not sure. It requires a bit more investigation to find out. And over here, we have the bottom of those capacitors we were looking at. And right here, you can see the power supply line coming in. So here's one on this side. At the very top, here's the other one coming in. This switch here just switches between 220 volt and 120 volt. It's a big gigantic switch. Look at the big filter coming in. Yeah, it looks really nice. Now, and there's another really cool thing here, and that's the output network. We can't really see it very well, but this section over here looks like that custom-made voltage divider, and all the feedback network is contained within this, and this is clearly something they have made. I don't think this is off the shelf, and everything is inside this tube. Unfortunately, we can't see it very well because it's all enclosed. But whatever they're doing there is conditioning the output, dividing it, providing the feedback in a safe way, because from here you still have to create a low voltage signal to go back, which is itself quite a bit of a challenge. And this thing does see plus or minus 20,000 volts with respect to the earth ground. Yeah, pretty complicated overall, but I can't wait to turn it on so we can play around with it. And here's the front of this instrument, and as you can see, it's pretty gigantic and it weighs a lot. The AC input is interestingly in the front of the unit. That's because the high voltage power supplies are in the back. In a way, this AC input is the lowest AC signal in this entire unit, because after this it goes into high voltage power supplies around 20,000 volts. And then we do have our power switch, of course, right there. Here's the business end of this. You can see how much clearance there is around this. And this is a special cable connector. The cable goes all the way inside of this and gets screwed down so that it has enough isolation. And then after that is the thick high voltage cable that comes out. The ground of the unit is the entire chassis. So there's a bolt in here to connect the ground. I have just connected this, but this is really not a very good way to connect this, because if you're relying on the ground to protect yourself, you want to make sure that this is solid, it is connected correctly. This is a reasonably solid connection, but generally you want a thick cable there too. At the top we have our input signal. This is the high impedance input to the amplifier, as we saw. There is output monitors here. You can monitor the voltage and the current that is going out, which is very nice. We do have a fault detection and a current limit, so you can limit the current up to 20 milliamp for the output there. And then there's an out of regulation status, just like any power supply. If it goes out of regulation, you will know. And there's also a TTL signal that you can measure, for example, to take some action. And this is useful because it also works on AC. And there's a dynamic adjustment here, but it basically changes the AC response of the output driver in case you want to drive a capacitive load from this output over here. Other than that, it's pretty self-explanatory. We do have this thing that you pull out to enable, and then when you push it in, it cancels or disables the output, and you can have the output be cancelled or disabled by an interlock or just permanently connected, and then you just press this button and it enables the output. I can tell you that this is very dangerous. I made a simple mistake with it while I was trying to measure something. I had the output connected to some resistors. I was trying to make a measurement around 100 volts. The output power supply was enabled, and I accidentally plugged into this the multimeter ohms measurement. And of course, when you want to measure the ohms, you have to apply voltage in here, and this instrument doesn't care. So as soon as I plugged in the ohm meter in here, several thousands or tens of thousands of volts appeared here, and it vaporized everything that was connected to it. So it's very dangerous, and perhaps the interlock is one way to avoid mistakes like that. Nonetheless, we're going to do some experiment with it, this time a bit more carefully. So let's measure some high voltage waveforms coming out of the amplifier. The setup is pretty simple. I have the input connected to the arbitrary function generator of the Tektronix 4 series, because these oscilloscopes all have a built-in ARP essentially, so we can use it to drive this. And then the output of that going through the high voltage cable is going through a Tektronix high voltage probe. This is actually one of the ones I've repaired on the channel before. This is a THDP0100. It can take about 6,000 volts, but it has 100 megahertz of bandwidth, which is quite good. There's another version of it which I have also repaired on the channel. Everything is directly connected. We do have to be quite careful because, of course, this can completely destroy this, because it can go to 20,000 volts, which is well above the rated value of this. So I have the AFG set up. Now this is a pretty loud instrument, so I hope that the noise wouldn't be too bad when we turn it on, but we should be able to measure some nice waveforms. And there's a procedure to enable the output. I like procedures, so we're going to go ahead and turn it on. There we go. We pull this guy out, and then if I press this button, the output will be enabled, and whatever is applied here is going to get multiplied by 2,000. So let's focus on the scope. And here's the screen of the Tektronix 4 series. At the bottom we have the time domain signal, and you can see that the vertical scaling is huge because it's scaled by the active probe. And at the top we have the spectrum view starting from 0 Hz all the way to 10 kHz. Now the entire ecosystem of the Tektronix oscilloscopes with the digital down conversion and all you can do in spectrum view is unique in the industry. It's just the amount of stuff you can do is extraordinary. If you've ever watched any of my reviews of these, hopefully you can appreciate it. This is a very simple test. We're only looking at the spectrum, and you can see a little bit of 1/f noise that's going to come from the active probe, as well as the instrument that we're using and the amplifier, which has no input right now, but this output is enabled. So let's go ahead and apply an input very carefully here. So if I go into the AFG setup, right over here, you can see that I have it set up to apply 1 volt peak to peak. Let me change this to a lower frequency. So let's say 1 kilohertz here. So 1 kilohertz, 1 volt peak to peak, it should become about 2,000. Double checking that and turn it on and check it out. Here's the sinusoid coming out, and it is 2,000 volt peak to peak, and RMS is 700, very nice crest factor, and the frequency is 1 kilohertz. And look at the THD. It's really quite good. I mean, this is a 2000 volt peak-to-peak signal being amplified linearly, and the THD is enormous. Now the number here is in dBm. That's because it's assuming a 50 ohm load, but of course it's not being terminated into 50 ohm, but the delta does represent the THD. Now we can make this larger, but remember this is a broadband amplifier. So what I can do is I can add an offset. If I add a 1 volt offset, very carefully here, it's just going to shift this waveform. And now look at the RMS, it's now 2 kilovolt because it's dominated by the DC. So it's just amplifying everything. It doesn't really care. So let's go back to 0 over here, and let's make this, push it to as far as we can. I think 2.5 will give you 5,000 volts. Let's double check here. If I make a mistake here, I will destroy everything. So here we go. Look at that. Here's our sinusoid, 5,000 volts peak to peak, and the THD is still pretty good. This is of course nowhere near the maximum this instrument can do. It should be able to do 40,000 volt peak to peak. And I can change the waveform shape. I don't have to use a sinusoid. I can put a square wave. Look at that, square wave, no problem. There's a little bit of overshoot over here, and the spectrum looks correct. I can put, for example, a ramp in here, and it would look like a triangular wave. Yeah, it's a perfect amplifier, of course. Now we can go back and change this. Let's go back to sinusoid. Let's increase that to 20 kilohertz. So we should still be able to maintain the signal at 20 kilohertz. There we go. Yeah, it dropped a little bit. And at 30 kilohertz, we're most likely going to drop even more. There we go. Yeah, we're beginning to lose bandwidth. But yeah, it's kind of meeting its specification. I'm not pushing it to its highest frequency, of course, but nonetheless, it is working beautifully. And of course, the instrument has no problem measuring that. I can't push it beyond this because I'm a little bit worried because each of those terminals cannot go more than 2.3 kilovolts above ground, which they're roughly sitting there right now. So we do have to be careful, but it is working perfectly. Now I do want to push that amplifier to higher voltages, and I need a different setup to protect everything, as well as be able to measure something that's in the order of 20,000 volts. Let's take a look at that. Now, in order to measure the higher voltages, we need some kind of a voltage division, and for that I'm going to be using this vacuum tube based capacitive divider. This is an HP model 452A, which I restored in one of the previous videos. It uses a vacuum tube capacitor with a much larger capacitor in the base, creating a division ratio of about 1,000. That means that the voltage appearing over here is just the AC version, whatever you put up here, but divided by 1,000. Now this is very nice because it has a very high breakdown. I can go to more than 25,000 volts on this. But even this has its own limitation because you can see there's an arc gap across here. If you go too high in voltage, you will arc across and it will certainly scale the head of you, but it will prevent the tube from breaking down. There's also a current limit because this is a capacitive divider. The amount of reactive current going into it is a function of frequency. So we're going to measure this at lower frequencies at around 200 hertz, even though you can really use this up to tens of megahertz. And the output of that directly goes now to a regular input of an oscilloscope. I'm using a different oscilloscope here just in case because that Tektronix 4 series is quite a bit more expensive. Nonetheless, this is still a very good oscilloscope too, so I like to make sure everything is connected correctly. So we are using the arbitrary function generator again, going back over here. This can put out up to 12 volts peak to peak, which means we should be able to hit 24,000 volt peak to peak, which is still nowhere near what this amplifier can do, but is significantly higher than we were measuring before. So here I have the ARP set to 200 Hz and 3 volt peak to peak, which means the output of the amplifier should be 6,000 volt peak to peak divided by 1,000. We should be reading a peak to peak voltage of 6 volts if everything is working correctly. Let's try that. And check it out, 5.96. I'd say that's pretty good. So the voltage divider is working quite nicely. This is 2.1 kilovolt RMS, 6 volt peak to peak, which means it is 6,000. Looking really good. Let's go ahead and increase that and see if we can maximize it and see what happens. There we go. I'm going to change the scale a bit. And here we go. Finally, 24,000 volt peak to peak. You can see it's 23.7. It's not quite 24. I can hear kind of a little bit of a corona discharge sound coming along. It's just electrons escaping everywhere because things are exposed. Very dangerous. But yeah, you can see the voltage divider is working, and at least it is working to 24,000 volts. And look, it's still sinusoidal, which is pretty amazing. It's a very dangerous thing, but a beautiful work of engineering. So because we have control over the frequency, we can do some strange things using this discharge tube. So I have right now the frequency at 2.5 kilohertz. This is going to be 14,000 volt peak to peak. We turn it on and we can see some activity. Now I'm going to keep increasing the frequency, and look what happens. You have some chaotic discharge in there. And as I increase the frequency, it's going to become more and more well defined. You can see it's still jumping around. I'm at about 10 kilohertz now. Now it's all over the place. As I go to higher and higher frequencies, so here, look at that, around about 25 kilohertz, it just stops. The frequency is too high for it to move around, so a particular path, a conduction path of ionized gas, kind of remains maintained, and it stays there without moving. If you hit just the right frequency, it just all of a sudden pauses like that. It doesn't look real. In person, it looks much more interesting, but you can see that it's not moving around anymore. Now think about what's going on. You have a flow of electrons that are hitting this gas, ionizing it, but they're not moving around anymore. That path is fixed because the frequency is so high. Really interesting effect. And I'm sure you want to know if this thing can spark over and survive. Let's give it a try. There we go. That's really loud. It's at 5 kilohertz. And there goes the resistor. You can see how much power this thing dumps into it. It has absolutely no mercy. And there you have it. I hope you enjoyed this detailed tutorial. It ended up being longer than I anticipated, but I really wanted to dig in and make sure that we cover a lot of different grounds. I hope you enjoyed it. Let me know what you think in the comment section. See you next time.